Hello friends, myself Jyotirmoy. Here we are going to discuss about the optical amplifier and its applications, functioning and types. So first of all, coming to the general application of an optical amplifier. First application is inline amplifier. So inline optical amplifier can be used to compensate for transmission loss and increase the distance between regenerative repeaters. And this is the block diagram of inline amplifier. Now next application is preamplifiers. So this optical amplifiers being used as a front end amplifier for an optical receiver, and a diagram of preamplifier is this. Now power boost amplifier is also one of the application of optical amplifier. So power or booster amplifiers application includes placing the device immediately after an optical transmitter to boost the transmitted power, and a diagram of power booster amplifier is this. And the lane booster amplifiers is also one of the application of optical amplifiers. So the diagram of lane booster amplifier is this. Now coming to the need for an optical amplifier. An optical amplifier is a device that amplifies an optical signal directly without the need to first convert it to an electrical signal. Reasons to use optical amplifiers are reliability, flexibility, wavelength division multiplexing, that is WDM, and low cost. There are three types of optical amplifier, and they are semiconductor amplifiers, erbium doped fiber amplifiers, and Raman amplifier. Coming to the semiconductor amplifier, it is based on semiconductor gain medium. It is like a laser diode where the end mirrors have been replaced with anti-reflection coatings. It is used in telecom systems in the form of fiber pictorial components operating at signal wavelengths near 1.3 or 1.5 micrometer and offering a gain of up to 30 dB. There are two types of semiconductor amplifier, that is Fabry-Perot amplifier and traveling wave amplifier. So this is the diagram of Fabry-Perot amplifier. So in this amplifier, incoming beam is reflected in the amplifier, and this is traveling wave amplifier, and in this amplifier end phases are AR coated or wave guided is tilted with respect to end phases.
Hello friends, myself Sajidur Rahman, and here I am going to discuss next part of this optical amplifiers, erbium doped amplifiers, erbium doped fiber amplifiers. So the main principle of rare earth doped fiber amplifiers is the same as that of lasers, excepting that such amplifiers do not require a cavity, whereas a cavity is required for laser oscillation. Advantage of EDSs are as follows. The active medium in an optical amplifier consists of a nominally 10 to 30 meter length of optical fiber that has been lightly doped, for example 100 parts per million, with a rare earth element such as erbium, yttrium, thulium, or praseodymium. The host fiber material can be started silica fluoride based glass or telluride glass. The operating region of this device depends on the host material and the doping elements. A popular material for long haul communication applications is a silica fiber doped with erbium, which is known as erbium doped fiber amplifier. In some cases, yttrium is added to increase pumping efficiency and the amplifier gain. Operation of standard EDFA is limited to 1530 to 1565 nanometer. So this one is the optical fiber amplifier. So here the one pump laser is using, two pump lasers are using, and the optical input and the optical output is showing. The isolator WDM is showing here. So this one is the erbium doped fiber amplifier. Now coming to the Raman amplifier. In a Raman amplifier, the signal intensified by Raman amplification. Unlike the EDFA and SOA, the application effect is achieved by nonlinear interaction between the signal and the pump laser within an optical fiber. These are two types of Raman amplifier, distributed and lumped. The principal advantage of Raman amplification is its ability to provide distributed amplification within transmission fiber, thereby increasing the length of spans between amplifier and regeneration sites. So this one is the typical Raman amplification system. So here we are showing a stimulated signal power. The stimulated signal power evolution along a 100 km fiber link for different values of on-off Raman gain, which is the increase in signal power at the amplifier output when the pump lasers are turned on. So coming to the necessity and concept of optical amplifiers. To transmit a signal over a long distances more than 100 km to compensate attenuation losses, initially it was accomplished with an optoelectronic module consisting of RX generator, equalizer and optical transmitter to transmit the data. Although functioning this arrangement limited by optical to electrical and electrical to optical conversion. So traditionally, when setting up an optical link, one formulates a power budget and adds repeaters when the path loss exceeds the available power margin. To amplify an optical signal with a conventional repeater, one performs photon to electron conversion, electrical amplification, retiming, pulse shaping, and then electron to photon conversion. Although this process works well for moderate speed single wavelength operation, it can present a data transmission bottleneck for high speed multiple wavelength system. Thus, to eliminate transmission delay problem, a great deal of effort has been expended to develop all optical amplifiers. Now, coming to the role of an optical amplifier in WDM network. WDM stands for wavelength division multiplexing. In traditional optical communication systems, optoelectronic regenerators are used between terminals to convert signals from the optical to electrical domain and then back to the optical domain. Since first report in 1987, the erbium doped fiber amplifier has revolutionized optical communications. Unlike optoelectronic regenerators, this optical amplifier does not need high-speed electronic circuitry and is transparent to data rate and format, which dramatically reduces cost. In the last dozen years, tremendous progress has been made in the development of EDFA components and technology, including the erbium doped fiber, semiconductor pump lasers, passive components and splicing and assembly technology. In the research area, an EDFA with a bandwidth of 84 nanometer was recently demonstrated. Using this high performance amplifier, long distance transmission at 1 terabyte per second was achieved for the first time. In the meantime, an enormous effort has been underway to incorporate EDFs into commercial optical communication system. After intensive laboratory research and development, this technology has become a very good one and supplied the first commercial WDM system, and these are the role of an optical amplifier in wavelength division multiplexing network. Thank you.